Hello, welcome back to your chemistry revision course. So we will be moving on to do some fractional distillation, so covering some other separation methods, which consist of fractional distillation, paper chromatography, and the noble gases, as well as covering some basics on electronic structure. So I just want to remind you that this is a 1 hour session. We have the rest of this week, we have the sessions on at 5 till 6. It's recorded and a recording will be sent to your parents. And any questions you may have, please pop them in the questions and use the questions or the chat and use this just for questions and answers. Thank you. Okay, so let's quickly, so yesterday we covered a bit about atomic structure. We did a little bit of balancing chemical equations and then looked at some we looked at some separation methods. Yeah, some physical separation methods. So we're going to start by balancing this other chemical equation, and just to recap and consolidate what we did yesterday, okay? So where do we start? We want to check how many atoms of each different element we have on the left and the right hand side of our chemical equation. So we learned yesterday that our left hand side was our reactants and that our right was our products. So then if we start by counting our atoms, so let's look at carbons, hydrogens, oxygens, so our three different atoms present, okay? So how many carbons do we have on the left-hand side? We have 5. How many on the right? We have 1. How many hydrogens do we have on the left? We have 12. So we're looking at this little number, aren't we? And how many hydrogens, do we have on the right? That would be 2. How many oxygens do we have on the left? That is 2. And how many oxygens do we have on the right? That is 3. Okay. So where should we start then with this one? So I see some questions have come through. So when we balance equations, are there always going to be the same elements on each side? Yes. So you always have the same elements on your left-hand side and on your right-hand side. Yep. So, and they must be balanced. So if you have 5 carbons on the left, you must have 5 carbons on the right. So today we are covering separation, some more techniques. So yesterday we did simple distillation. Today we'll be doing fractional distillation, which a lot of you were asking about actually, and also paper chromatography, which hopefully you've met, and then doing some stuff on the electronic structure and finishing by looking at the noble gases. And yeah, brilliant. Whoever suggests starting with a carbon, that's exactly where we're going to start. Today we're not going to do a Kahoot. There'll be some practice questions at the end, though, where you can send in your answer to the chat. And the number next to the hydrogen here, it says 12. Sorry, it's a bit messy. So let's start with the carbon, like it was suggested. So if we've got 5 carbons, we need 5 carbons on the right-hand side. So we're going to put a 5 in front of the carbon. That's going to change the number of carbons and the number of oxygens on our right-hand side. So now, how many carbons are we going to have? 5 times 1 is going to be 5 carbons. And then 5 times 2 oxygens, because in our chemical formula we have 2 oxygens, is going to give us 10 plus the 1, which is going to give us 11 on this side. Okay, so the next thing to do is balance our hydrogens. Yeah, so on the left hand side we have 12 hydrogens, but on the right hand side we have our 2. So in front of our H2O, in front of our water, we're going to put a 6. That's going to now give us, what's that going to give us? So 6 times 2 is going to give us 12 hydrogens. But now our oxygen number is also going to change, because in the chemical compound that we have changed, we have also oxygen. So now 6 times 1 oxygen is going to give us 6 oxygens. We've still got our 10 oxygens from this part. That means we're going to have 16 oxygens now on the right-hand side. Okay, so therefore, what are we going to put in front of this O2 to get to 16 oxygens on the left-hand side? Do people have any answers they want to post in the chat? Yeah, I can see lots of correct answers. Brilliant. So we're going to put 8, because 8 times 2 is going to give us that 16 value that we want. Okay, so that's our little recap of this thing. So it's 16 oxygens because here, right, we have 6 times 1 oxygen in this chemical formula, and then 5 times 2 oxygens in this. So 5 times 2 gives us the 10, 6 times 1 gives us the 6, 10 plus 6 is equal to 16. Okay, so let me quickly look through the questions. Okay. Does it matter if we start with the oxygen first, then the carbons? So this is actually, some of you may recognize a combustion equation, and usually you start with your carbon. If you start with the oxygen, it takes more time because you keep, as you can see, there's quite a few steps. Once you change one element, you need to go back onto this side and change that one, and so starting with the carbon is the best place instead of the oxygen. Okay, so let's move on to the next questions. So we'll be able to practice more balancing equations in our 5th lesson. Is there any tips? Balancing equations in general is actually, I agree, quite a confusing topic. So I think just take it in steps. Do these steps like I've done here, and always write out how many atoms you have. And yeah, I'd say just take your time, because it is one of the confusing parts which you can easily make mistakes on. And we'll cover more balancing equations in the last lesson when we're practicing exam techniques. Okay, so now let's move on to our topic for the day. So fractional distillation, paper chromatography, and noble gases. So we met distillation yesterday, right? And some of you are very well aware of fractional distillation. So distillation, the one we did yesterday, is just simple. With fractional distillation, we're separating. So yesterday, we were separating a solution, right? We had salt dissolved in water, and we wanted back this solid. So that's why we just evaporated our liquid, and that was fine. But in this case, we want to separate liquids, and liquids usually have a much similar boiling point. So in your yesterday one, say in the salt solution, the salt is never going to boil off because the salt boiling point is far higher than the water boiling point. So it's just going to be left as a solid at the bottom. However, with mixtures, they have fairly similar boiling points, and so we need to use this fractional distillation technique. So they have similar, but they are still different. A fractionating column helps with this separation, and the way it works is that substances with lower boiling points condense at higher points in this fractional column, which we're going to see now here. So a lot of questions are coming through. So a miscible liquid is a liquid that dissolves in one another. So if, say, you might have done this experiment at school, say, you might have put water and then oil. And what you form are 2 layers, right? So your water goes on the bottom, and then you have the oil on the top. Yeah? So when this happens, that is a non-miscible liquid, okay? But however, as we see here, right, ethanol and water, the ethanol and water mixture, it just forms a whole liquid. It's like they have fully mixed together, as opposed to having this separation, as can be seen when you have oil and water. So that's a miscible liquid, something that can mix without separating and forming layers. Okay, so people are asking to see the slide again. If you guys want to take the notes down quickly, we'll move on to the other page. because then we'll just explain how it works with this column. So there's a question about, would the ethanol and the water be chemically mixed? I don't really understand what you mean by chemically mixed. So there won't be chemical bonds between the water and the ethanol. It's just they mix well together. So oil and water, they don't mix together. These two mix together because they have intermolecular forces. Okay. So miscible means that they can mix. They can mix fully. Why is oil non-miscible? Because there is unfavorable interactions. This is actually stuff that you would probably do if you did A-level chemistry. The water and the oil, they don't want to interact with each other. Yeah, let's get back to this slide. Okay, so let's look at this. We have this part, so you should see a lot of similarities with our structure, with our fractional distillation, well, with our distillation yesterday. So we have a beaker, we have our condenser, but this part is our big difference, okay? So the way that this works is that the temperature is very different at the bottom to the top. So at the top, it is much colder, much lower, the temperature is much lower, and here the temperature is fairly high, okay? It's low. So substances with a high boiling point are going to condense at the bottom of the column, okay? Because say if you've got an 100-degree, so if the boiling point of water is 100 degrees, and as soon as this fractional column is, say, at 99 degrees Celsius, it's going to condense because the temperature is below its boiling point, okay? Does that make sense? So therefore, at the bottom of the column, substances with a higher boiling point, condense and they drop back into the flask. So in this flask, when you're separating an ethanol and a water mixture, you're left with your water in that flask. However, because ethanol has a lower boiling point, it's carried through the fractional column and goes into your condenser. And then in this condenser is where it forms liquid ethanol, and you collect it like back what you saw with your simple distillation. Okay, so that's the method. The key thing to remember is that at the bottom of the column it is much warmer than at the top, and at the bottom the substances with the high boiling points condense, and the low boiling point substance is carried through. And there's some questions coming through, so I'll take a quick read of them. So what does the water in and water out do? So this is what you use to cool down. So here, right, what you're passing through is a gas. And how do you get a gas into a liquid? You condense it, right? So you need to cool it. That's what you're doing when you're condensing a gas. So what the water in is cold water comes in and it fills this condenser up, okay? Fills this condenser up with cold water. So then when the gas passes through this condenser, you get it forming the liquid. It gets cold and then forms a liquid. So all that this is doing is you push the cold water in, and at the top you push the cold water out, and it goes upwards to ensure that this whole condenser is filled with water. Okay. Yeah, so the bottom of the fractional column is hotter. Brilliant. So if there were 3 liquids mixed, we're going to see on the next slide what happens. So that's where we can talk about the example of crude oil that many of you guys should have met in school. So miscible liquid means that the liquid fully dissolves in the substance. Yeah, so the boiling and condensing point are the same. So if it boils at 100 degrees like water, at 100, so when it reaches 100, it starts boiling. But if it's anything below 100, it's going to condense and form the water. So no, the liquid with the lower boiling point, it condenses after the higher boiling point. Because if you think about it, if you have a boiling point of say 50, it's going to condense when it reaches 50 degrees Celsius or below. Okay, but at the bottom, we've said that it's much hotter. So therefore at the bottom, it's going to be, the temperature is going to be higher than 50. And at this point, it is still above its boiling point. So it's still a gas. So it's going to still go through the condenser. If the two things have the same boiling point, you can't separate them, but no substances have the same boiling point. All substances are slightly different. It's much harder to separate substances that have very similar boiling points. But in the case of ethanol and water, ethanol has an 78 degree boiling point and water has a 100 degree boiling point. So therefore you can definitely separate them. Okay. Let me just check the question answer bit. So the water out is literally just, so obviously if you just had constantly water in here and you couldn't, and it wasn't changing, the steam is going to heat up the water. That's why you need a constant flow of water. So the water in goes through the condenser, it absorbs the heat from the gas because it's cooling down the gas, yeah, and then it pushes the water out. So constantly this water in the condenser is being replaced, and it doesn't allow this water to heat up because you want this water to be really cold to allow this condensation to occur. So by constantly replacing the water, you're keeping the water in the condenser at a low temperature. Does that make sense? If there were oh sorry, I've already said that one. No, you don't need to know how cold the water has to be in the condenser. It's just at school you would connect it to your water supply. Okay, so let's move on to see. So have many of you guys talked about fractional distillation at school in terms of crude oil? So crude oil, as many of you should know, has lots of hydrocarbon fractions. So this may be a bit advanced for some of the students, but it's just different substances in our crude oil. Yeah. So each different substance has a slightly different boiling point. And can you see these like different levels? So whenever the substance reaches its boiling point, it condenses. So you put in the evaporated crude oil, the one with the highest boiling point condenses here, and you collect the liquid on this tray. So then the rest of the crude oils continue going up until they reach their boiling point. So the next one with the highest boiling point is here, it condenses here. The next one, which is diesel, will condense here. And then at the top, this is petrol, has the lowest boiling point of all of these. As you can see, your temperature is decreasing from the bottom to the top. Okay. Yeah, exactly. Yeah. So the difference between fractional distillation and simple. So fractional distillation is used to separate miscible liquids. So liquids that are fully mixed and you can't see that there's two liquids in them. You just have to know. Otherwise, if liquids are not miscible, you can see this difference. You can always see a line where you see that they're not fully mixed. And yeah, so in fractional distillation, you have this column, this fractionating column, okay? Whilst in simple distillation, you go from the evaporator straight into your condenser. And this fractionating column, it allows you to separate the liquid because at the bottom, it is much warmer than at the top. So therefore, those with a high boiling point condense down here and the rest continue to go through the column. Sorry, I'm just reading the questions. So if the substance had different boiling points, then how would separate? Sorry, I don't understand that question. So what's the definition of the distillate? It's this part in this part. This is the distillate, whatever you've collected after it goes to the condenser. So the thermometer, it checks the boiling point. So like I said, the ethanol boiling point is 78. So at this point, because it's evaporated ethanol, the boiling point is going to be 78 degrees. So we're just checking that we've reached hot enough when we're doing this distillation, just to make sure. Okay, so I think we're ready to move on to the next subject. Okay, so there's a question, why is the boiling point the same as the condensing point? So if at 100 degrees, so we have our water, and we heat it to 100 degrees, and at 100 degrees or above, right, any temperature, 100 degrees or above, it starts evaporating. Yeah? So therefore, at 100 degrees or any temperature below, it starts condensing. So 100 degrees is a bit of a threshold. So you could think of it as when it reaches 101 degrees, it starts evaporating. And when it reaches 99 degrees, it starts condensing. Sort of, if that makes sense. But 100 degrees, you can say that that's the condensing point as well, because anything below 100 is going to make it condense. Yeah, brilliant. Hopefully that made sense. Okay, so now let's move on to paper chromatography. Hopefully many of you guys have seen this topic at school, and hopefully you've had the chance to do the experiment, because that's quite a nice experiment to do. So paper chromatography. It's separates mixtures of solutions. Over a mixture solution. So it works because compounds in a mixture dissolve better than others in a solvent. So if we've got like a mixture of a liquid with lots of different substances, they dissolve differently in different solvents. So the relative solubility of a component making up the mixture in a solvent determines how far they travel up the paper. So this will become a bit clearer when we look at the example. So in this case, let me just, there's lots of questions. Sorry, just look at the question again. So no, you don't need to know the two diagrams off by heart. You need to be aware, and it's quite good to be able to draw it. So know where the condenser goes. So what does fractional distillation do? It separates miscible liquids. So liquids that mix fully but have different boiling points. Okay. So how do you assign different colors to chemicals? That's not important. So just the different substances that have been mixed together have different colors in the example across the page. So hopefully people are ready for me to move on to the next page then. Okay, so let's look here. So how does it work, right? We get a capillary tube and drop our substance onto the bottom line. Then we put our paper in our solvent. So this is our solvent, and the solvent is absorbed up the paper, as we can see here. And then so this orange color and this blue color is made of different colors, which are different substances. These different substances have a different solubility in our solvent, which is water. So the more soluble the substance is, the higher it gets dragged up across the paper, okay? So in this case, which color is more soluble? The yellow or the red? So obviously, as we can see, the red has become higher up, has reached higher. So therefore, the red is more soluble than the yellow, okay? And in the other case, so which colour is the most soluble in water in this case? Do people want to quickly jot down some answers? Yeah, perfect. Exactly. It is blue because it's reached higher up the thing, up the paper. So we put it on this paper chromatography paper. Sorry, I'm just quickly looking at the questions. So the size of the paper doesn't matter. And yeah, whoever this is back to fractional distillation, perfect. So the boiling point's different due to the length of the hydrocarbon chain in crude oil. Very well done. That's really good. Just did that. Okay. So a solvent is something that can dissolve a substance. So if say you have so say water and sugar, the water is your solvent because it can dissolve this sugar in it. Yeah. But otherwise, yeah, solubility is how much it can dissolve, how well it dissolves in this substance. So what would happen if the green line was longer but the blue was higher? The length of our dots doesn't matter. Okay, so let's continue with this topic then. So we're just going to get on to RF then after this. So yeah, that's how it separates. So key thing to remember is that the more soluble substances, the higher it goes up the paper. Okay, so now let's look at this slide. So another thing about paper chromatography, it allows you to see what of the same substances you have in your mixtures, okay? So here we have a purple and a green dye, yeah? So can people tell me what substance, what colour is in both of purple and green? So both of these, yeah, perfect, they both have blue. So they both have the chemical that makes up this blue dye, right? And in this case, in the purple one, we have red, and in the green one, we have yellow. So paper chromatography lets you tell which two compound or which two substances are the same. So if we were looking for this substance, sorry, let's label them A, B, C. Oops. A, B, C. So we want to identify which of B and C, which is the same as A, which has the same chemical composition as A. So because these two dots are lined up exactly, we know that A and C are chemically the same. They have the exact same substances. Okay, so now let's talk a bit about RF values. Oops. Let's go back to this one. So with RF values, we need to always ensure we know where our solvent has reached up to which point. Okay, so in this case, we say that our solvent has gone all the way up to this point. And then the RF value is the distance from the substance we're looking at divided by the total distance to this point. So is there a rule on here? Sadly, I don't think so. You'd have to do this, say, on paper. But yeah, so you get your ruler, you measure this distance, and then you get your ruler, you measure that distance, and it's the shortest distance over long distance. If we call this one distance x and call this one distance y, it's x over y. Okay, so like if we want to find the RF, so RF in this case equals x over y. If we want to find the RF of the yellow dot, we're going to measure the distance from our baseline to the yellow dot, the distance from our baseline to the solvent front, which is this top line. So the solvent front is where the solvent's reached. And then we're going to say this is A and this is B. So our RF is what? People want to jot that in the chat? What's the RF then? So RF is retention factor, I think. Yeah, brilliant. A divided by B. Yeah, you can. So someone says, could you say that red is more soluble than yellow, even though they're in different substances? Perfect. You can say exactly that because your solvent is the same. So let's just say the solvent is water. So if the solvent is the same, brilliant. Can two different chemicals reach the same height? They wouldn't reach the same height if they're two different chemicals because they have different solubility. Yeah, perfect. You're all showing good understanding, okay? So let's move on to the next topic. People have any more questions? Do you make RF into percentage? It doesn't really matter. Usually you give it as a decimal point. Okay, let's move on then. So electronic structure. Electrons are arranged in shells, each representing a different energy level. Does that make sense? So a shell is that circle that you should have seen before. So if we represent the electrons in hydrogen, so our first shell is this circle, okay, which will hold one electron because, as we know from yesterday, hydrogen has one electron. So electrons are arranged in shells. The shell that is closest to the nucleus always has the lowest energy, and the energy levels, the energy of these shells increases as you go further and further out. So another thing to note is that the first shell holds only 2 electrons, and then from then on, the shells hold up to 8 electrons. Okay, what that means is, say for helium, as we know, we have only 2 electrons in helium, so therefore we filled the lowest shell. Okay, and then from then on, if we take another example, do you have another example? Oh. And then if we say take oxygen, oxygen has 8 electrons in total. So the first one is going to have its full 2 shells, and then the second one is going to have the rest of the electrons, which will be 6. Okay, so that's a basic on electronic structure. So yeah, electrons are arranged in shells, which is the circles, and each shell represents a different energy level, and the one close to the nucleus is lowest in energy. The first one, which is lowest in energy, holds 2 electrons, and it's a full shell after that. And then from then on, shells hold up to 8 electrons. You only need to know how to do the electronic structure for the first 20 elements, because after that it gets much more complicated, and you don't need to know it. So here are some examples. So for the hydrogen, as we've seen, it only has 1 electron, so therefore it's just got this 1 electron in its lowest energy shell. So in the boron, the lowest energy shell, once again, holds 2, and then we start filling the next energy shell, which can hold up to how many electrons? If you want to jot in how many can the second energy shell hold up to? Perfect, lots of 8s. Amazing, yeah. Well done to the 2,6 electronic structures, brilliant. So what are dot and cross diagrams? So dot and cross diagrams are a way of expressing your electronic structure, like we can see here. We put our nucleus in the center of our atom, and then on the outside we have our electrons orbiting in different energy shells. Okay, so at the bottom you might see the electron configuration is written with numbers. So the way you do that is you just write the number of electrons in the first shell and then the number in the next shell. So we've got 2 in the first one, 3 in the next one, with a comma in between. So like aluminium, we have 2 in the first shell, 8 in the next one, and then 3 in the outer shell. Okay, so that's how you write down your electronic structure. So if we say take fluorine, do people want to try write down? So it's got 7 electrons. Do people want to jot down the electronic structure in this notation? Fluorine. Oh, sorry. My bad. It's 9. Sorry about that. It's actually 9 electrons in that. Yeah, brilliant. So it should be 2, 7. Amazing. Well done, everyone. Okay. So yeah, these are a couple of examples of how to draw them. So now let's talk a little bit about the arrangement in the periodic table. So groups, they tell you how many electrons the atom has in its outer shell. So in the case of, say, calcium, how many electrons does it have in its outer shell? Brilliant, 2, perfect, okay. You can either look at this number at the end, or you can look and count them in this way, yeah? What about boron? How many outer electrons does that one have? Yeah, someone's, okay. So we should be able to see 3 in both the number and the cross-dot diagram representation. Okay. So yeah, groups tell you how many electrons are in the atom outer shell, and then chemical properties, especially the reactions, is determined by the number of electrons an atom has. So an atom, we've said, can hold up to 8 electrons, so 2 in its lowest energy shell, right near the nucleus, 8 in any shell after that. So the most stable conformation is when you have a full shell. So hydrogen's a bit sad because it only has 1 electron in its outer shell. Yeah, but helium, and how many electrons does it want then? It wants 2 in its outer shell because it wants a full shell. Helium, on the other hand, we know that helium has 2 electrons, therefore 2 electrons in the in its shell, so in its lower shell, and it is really happy because 2 electrons is a full outer shell, so therefore it is a very stable configuration. Brilliant. See, I can see lots of great information. People really understand this topic. What about the elements on the periodic table that have really big atomic numbers? You do not need to worry about that in your GCSEs. You only need to know up to 20, electronic structure of 20. Why is there weaker force from? So, okay, next part. So yeah, let's talk about the periodic table quickly. So if we took an atom from, say, sulfur, how many electrons does it have in its outer shell? All we need to do is look at the top, yeah, and see it's in group 6. So we know straight away it is 6. So what about barium? How many electrons does it have in its outer shell? Yeah, brilliant. I can see lots of 2s. And silicon, how many does that have? Brilliant. Okay, I think people really get that. Any questions? Just look through the questions. Dun, dun, dun. And yeah, the recording will be sent to your parents. Okay, let me just see the chat quickly. So we're going to be covering group 1 and group 7 in tomorrow's lesson. So you've got that to wait. What's the key points of fractional distillation? We can quickly cover those at the end if we have some time. So can you please stop asking that question? We'll come back to it at the end. But yeah. Dun, dun, dun. Okay, so sorry. So noble gases, group 8. Now we've learned about a little bit about our electronic structure, we can talk about our noble gases and why they are so unreactive. So key things to remember about our noble gases is just how unreactive they are. All atoms, they all want to have a stable electron configuration, which means they have a full energy level. Yep. So a full energy level is either 2 electrons in its outer shell or 8 electrons in its outer shell. So if we look at the noble gases, they all have a full outer shell. So therefore, they're all really stable and they don't need to undergo any reactions. So they don't have any tendency to react because they're not trying to modify their structure. They're not trying to gain any electrons or lose any electrons to get this full outer shell. So they are completely and utterly happy in the way they are. And usually say helium, it doesn't come like hydrogen, H2. Helium's just helium, neon is just neon. They all come as just single atoms that form this element. We will be covering transient reactivity tomorrow. Yeah, so no, you can call the noble gases either group 8 or group 0. We can quickly, I can show you some dot cross diagrams. Is there a shorter way to balance equations back to the start? Not really. A lot of that is just chemical intuition, but I'd say the best thing is to count up your atoms on the left and the right. But yeah, questions about group 1 and group 7 will all be covered tomorrow, so make sure you come along to the lesson and we'll find out about their unstableness and about their reactivity trends. So I'll just look through the questions again. So another question is, how can someone tell what the electron capacity is in a shell is? For example, the 5th or 6th shell. This is not something that you need to know for your GCSEs. You literally just need to know the first 20 elements and how to do their electronic structure. This is much harder stuff for if you do A-level chemistry, which would be great. Does a cross? So the cross does not mean it's sharing in the dot cross diagram. It's just representing an electron. So I'm still loading through the questions. Oh, you don't need to memorize the first 20 elements. You just need to know how to do the electronic structure. So you just need to know how to show the electronic structure of the first 20 elements. That's it. You don't need to memorize them. You don't need to know how radiation affects the electronic structure. Okay. Look at the chat. Yeah, you will get periodic table and exam. Okay. So which exam board is this? This is on every exam board. Knowing the trend, the noble gas, knowing electronic structure is common to every single exam board. It's not specific because this is like fundamental chemistry that you all need to understand. Sorry, there's lots of questions coming through. I'm sorry if I haven't answered your question. It's quite hard to keep track of them all. So what are the noble gases? We'll explain it in one sentence. Very stable elements that do not want to react as they have a full outer shell. Okay, so yep, that's all you need to know for noble gas. Now let's try going over some past paper questions. Hopefully you can all see this okay. That's a bit blurred. Zoom out, maybe it'll be a bit better. So The electronic structure of the atoms of 5 elements are shown in the figure below. The letters are not the symbols of the elements. Choose the element to answer the question. Each element can be used once, more than once, or not at all. Use your periodic table to help you. Okay, so we're going to have to keep clicking to the periodic table. So which element is hydrogen? Let's go back to our periodic table. How many electrons does hydrogen have? From our periodic table, we can see it is 1. So therefore, we now know that hydrogen has 1 electron. Which element do we think it is, therefore, in question 2? Yeah, brilliant. B. Well done to everyone who said that. Okay, next one. So which element is a halogen? So do we know what a halogen is? Do we know what group halogens are? Yeah, brilliant. So whoever says group 7 is brilliant. So tomorrow we're going to be going over this. So yes, group 7s are our halogens. And because they're in group 7, we know that it has 7 electrons in its outer shell. So out of these 5 elements, which one is going to be a halogen? Brilliant. So everyone who said D, amazing. Well done to you all. So yeah, if we just count out the outer electrons, that's 2, 4, 6, 7. Exactly what we want. Dun, dun, dun. Yeah, this is in triple science for sure. So we're not going to do a Kahoot today, but we'll have a Kahoot ready for tomorrow. Okay, so next one. Which element is a metal in the same group of the periodic table as element A? Okay, so this one's a bit tricky. So we need to figure out what is element A. So in which group does element A belong to? How many electrons does it have in its outer shell? So we can see it has 1. Brilliant. It is lithium, whoever said that. It has 1. So which is a metal in the same group as periodic table A? So both element B and element E have 1 electron in its outer shell, don't they? Can we see that? 1 electron, and obviously the other one is 1. But can people tell me what is element B? What have we already said that element B was? Exactly. So we know that element B is hydrogen. Therefore, it can't be element B because that is a non-metal. Okay, it's really important to remember. B is a non-metal. So therefore, the metal that would be in the same period as A would be element E. So with period A, we're looking at the group 1 because we have 1 electron in its outer shell. So anything below lithium would be an answer. Okay. So then last, which element exists as a single atom? So do people want to try that one? Which element is going to be? Yeah, brilliant. Element C. Perfect. Because element C, in element C, we have 8 electrons in its outer shell. Yeah? And 8 electrons is a full outer shell, so it is a very stable configuration, which is exactly what we want. So brilliant. It is element C. Yeah, because it is a noble gas. So now let's look at this question. This is quite a fun question. So we're doing some paper chromatography to find out which colorings were used in her favorite sweets. The diagram shows some of her results. So give the color of a sweet which contains only 1 coloring. So if we just have 1 substance in yeah, perfect. So exactly, yellow or red is a sweet that contains 1 coloring. Perfect, because they've just got 1 dot, that we haven't separated anything from anything. Okay, so name 2 sweets which contain 1 of the same coloring. So which sweets contain 1 of the same coloring? So we look at our dots and we see which dots match up to the same length. So we look at this one. Oh, and look, so these 2 match up. So therefore, yellow sweet and green sweet have the same coloring, but also red sweet and purple sweet have the same colouring as well because they also match up. Yeah, brilliant. Lots of you guys are getting it. Let me just quickly look through the answers. So through some questions. Yeah, so people are answering. So if people want to say use the chat for their answers and the question and answer for their questions, it might be good. Brilliant. So many good answers. Well done, everyone. So fill in the results you'd expect to get for the orange sweets. So we need to think what colours make orange. And then we just draw that on. So what colours make orange then? Yellow and red. Brilliant. Okay. So what would it look like? We just look at the yellow one, we draw a dot where the yellow one comes up, and the red one, and we draw a dot where the red one comes up. Yeah. So which liquid would be used to separate these colourings? So we just need a solvent that, yeah, brilliant. Water is a great answer. Well done to everyone who's coming up with that. Exactly. Any questions quickly? So the RF value is the retention fraction. So it stands for retention fraction. Do you need to know which two colours mix to make a colour? Not really. I don't think this kind of question would come up on a real test. It's just to know how to show it. Sorry, retention factor. That's what I meant. Okay. So let's do another question then. Give two uses of chromatography. So as we've seen, it's to separate two substances, and also it can also be used to see whether two substances have the same mixture. Yeah, brilliant. Identify the dyes in the substance and see if two dyes have the same substances. Name the two faces. Yeah. Brilliant. So the two phases are mobile and stationary. Perfect. Okay, we'll come back to why do we use fractional distillation in 2 minutes. Complete the equation. So RF of the substance, so the length of the substance divided by the total length of the solvent front. So a pure compound will just have, yeah, brilliant. One dye will be present. Yeah, brilliant. So X or Y for my example. Well done, everyone. Perfect. Okay, so this one's a nice and explaining why, an explanation. So lithium, sodium, potassium are all in group 1 of the modern periodic table. So the group number, what does that tell us? So we need to say group 1, yep. They have 1 electron in their outer shell, perfect. And all lithium, sodium, and potassium have 1 electron in the outer shell. Therefore, they are in, yeah, group 1. Amazing. Well done, everyone. Oh, wow. Lots of colours are coming through. Lots of questions are coming through. Okay, let's see what the next question is. Okay, so this was another one on chromatography. This one has a lot more data though. So we've done our chromatography thing, we've ran it, and now we want to identify the Y to the other dots. So we want to figure out which substances Y is made up out of. So do people have any idea? Can they match up the dots? A, B, C, F. Okay. Brilliant. You're all giving great answers. However, this one slightly, I think, confused people. C, D, D, and E. Okay, so whoever says D and E, you would be correct. So although the dots, right, they match up with lots of different ones. So yeah, you're correct that this one dot of Y matches up with F, D, and B. However, in B, we have these two other dots. Although this dot matches up, we don't have this bottom dot, do we? We don't have this bottom dot here. Yeah, so therefore it can't be B, because if it was B that made up Y, we'd have this additional dot at the bottom. Okay, so in the same way, although some of say E does match up. Oh, sorry, it would be C. It would be D, E, and yeah, it would just be D and E. So yeah, although say F matches up, we would expect to have this dot here, yeah, and we don't have that dot, so it can't be F as well. Does that make sense? So why does C match up? C matches up here at the top. Can you see this top one that matches up? Yeah. However, this bottom one, it doesn't match up, so therefore it can't be C. So how does it match to D? Dun, dun, dun. Can you see these two dots match up, this one and this one? Yeah, so that's why it matches to D. And it matches to D because this dot matches with this bottom dot and this top dot matches with this top dot, okay? So now let's finish here, but we're quickly, well, before we finish, we're gonna quickly cover the pointers of fractional distillations. And we can just quickly look over that question tomorrow if people want to. It was quite a confusing paper chromatography question. So what was the question on fractional distillation? Dun, dun, dun. Why do we use fractional distillation? So we use fractional distillation because we want to separate two miscible liquids. That's the most important thing to remember, miscible liquids. And so two miscible liquids are liquids that can fully mix together. You don't see any sort of difference in the two liquids. So that's when we use it. And how does fractional distillation work? So our two miscible liquids, they're going to have different boiling points. So therefore, they're going to condense at different points. Yeah. Does this only work for crude oil? No, it works for any substance that has different boiling points in the liquid mixture. So miscible means it can mix fully. As we said, water, we see a line. If this is water and this is oil, they do not mix. The oil does not go into the water. A fully miscible liquid, you can't see any difference between your two liquids that are present in the mixture. They have mixed together, just like salt is fully dissolved in water. You can think of a fully miscible liquid as one liquid dissolved in another. Okay. The key points are the bottom of this fractionating column is hotter than the top. As you can see, this top is blue, it's colder. So hot is at the bottom, cold is at the top. So the fractions with the highest boiling points, they condense at the bottom. The fractions with the lowest boiling points, they condense at the top. And therefore, you have a separation of your miscible liquids. Those are your key points. So high boiling point, condense at the bottom. Low boiling point, condense at the top. Bottom of the fractionating column is hot. Top of it is cold. And the difference between simple and fractional is that in fractional, you have this fractionating column. Oh, where is it? It's up here. Yep. So fractional, you have this fractionating column used for separating miscible liquids. Simple, you just go straight from this into your distillating apparatus, into your condenser. And that is when you're separating a dissolved solid from a solvent. Okay. So I think that's all we've got time for today. You can find the recording of this. It will be sent to your parents, and it's also on the MyTutor YouTube channel. But yeah, hopefully see you tomorrow, 5 p.m. again, and we'll be covering group 7 and group 1 and the trends down there. Have a lovely evening.